thank you all for coming. Those of you pouring in, I'm sure you know what you're here for. It's a white paper deep dive, yet again, brought to you by Dad. So you know it's going to be fire. And today, we're going to be talking about the InterPlanetary File System, or IPFS, a content-addressed, version-controlled, peer-to-peer file system. And if none of those words mean anything to you, then hopefully by the end of this, you'll know what they mean. Who are we? I'm sure everyone on the call right now knows this is honestly just for like the folks watching at home. I'm Andrew Kirillov. Simon, you want to introduce yourself?
I'm Simon. Yeah,
Good.
I'm Simon. Yeah.
That's all there is to it, folks. So yeah, go ahead. If you guys have questions, just type them in the chat. That's easiest for us. There might be like periods when we ask for questions, but kind of just default to the chat. In fact, is there stuff in the chat already? Loki. Fire.
Yeah. They just, yeah.
Just some hype.
No,
okay,
some hype.
so to go over what's going to look like today. So first we're going to talk about like the motivation for IPFS, why PFS, right? Why do we need it? Then we're going to talk about some predecessors and background technologies, because it's really important to understand with IPFS that while there are novel parts to it, it's really kind of similar to Bitcoin in that it's just a very creative and innovative way to like take some existing technologies and make them work together. So then we're going to do like a quick overview on what those technologies are in the pieces of the puzzle section. Then we're going to take like a closer technical look in how it all comes together. And finally, we're going to be looking at the potential uses and like the implications, evaluations and applications, etc. So to kick things off, Simon, you want to take it away?
Yeah, sure. So first we want to talk about why do we care about this IPFS thing? And actually, let's start with what is this IPFS thing? Great. So you might saw the name InterPlanetary. The context is that, you know, if someday the humans get on Mars, we set up a place there and we want to see the internet, but the internet is still on Earth. And it takes about 4 to 24 minutes for a signal to transfer between Earth and Mars one way. And that's going to take 28 to 48 minutes in total. So if you want to check a meme page or download like a cat picture, it's going to take a long time. And if you do this every day, you will be like, I'll be driven crazy because I don't want to wait for like half an hour for something to load. So is there any way we can make this information transfer faster? And that's kind of the motivation behind this InterPlanetary name. But really, why do we need this? Like, I mean, we're not going to go to Mars really quickly. And on Earth, I mean, the internet connection isn't that slow. It's pretty fast. Well, it's because the current web and HTTP technology are not good enough with the increasing demands. Data sets are getting larger and larger, and it's going to be a scale of petabytes in the future. And also version controlling and linking data sets are very, very painful. If you want data sets from multiple organizations compute across them at the same time, that's going to be also really painful. And increasingly, we're getting higher definition videos, and with future headsets like AR headsets and VR headsets, we need high definition media stream all the time. And our current system is not good enough for that. Even we have like 5G and better infrastructure, it's on the protocol level, it's still slow, not fast enough. And the other more important and realistic thing is that a lot of the websites are gone after, let's say, usually it's about 100 days. And in some areas of the world, some websites are censored and you're not able to visit them. And there's no way really around it than, let's say, a VPN, but sometimes those could be dangerous or not work as well. So there's a lot of problem with the current web. But I want to go into a more detailed example. So how do we actually access the resources in our current internet right now? We access by the location. So Andrew want to get a cat picture. He goes to this, I made this website up, but he goes to this mail.cat/cat.image, and he found the cat picture and save it to local. Let's say I want a cat picture too, but I'm not able to visit that website for whatever reason. Maybe my I got blocked from that website, or the website just shut down. But I know actually Andrew has the image already. Is there any way I can actually get it from Andrew since he has it locally? Well, in this case, I actually know Andrew, so I'll probably ask him, did you download this cat picture before and can I get it? But in most of the cases, everyone hosts a lot of local files on their computers, but we might actually need something from your computer, but I don't actually know you, or you know you have the file on your computer. But if we can just kind of take storage from other people's local storage that already downloaded, and that's the resource we want, that will make our world a lot faster. And if the websites go down, it doesn't really matter because someone has it already. So that's kind of the intuition that, let's see, can I flip? Oops. Yeah, so what we want is, I don't really care where the cat picture come from. I just want the cat picture. It could come from like woof.dog.com. Like it doesn't really matter. So we want to create a file system that can do that. We want to have it, we want to have the address of the file, not based on its location on which server it hosts on, but rather we want to find it based on its content. And we'll dive into the technical details of that, how it happens later. And we want to create a file system that can handle these challenges, such as, you have a lot of data that you want to access, but you also want it to be accessible everywhere, no matter what kind of blocking server address or limited network partitions, such as between Earth and Mars. And you also want it to be fast, because if it's not fast enough, we're just going to stick with our good old HTTP. So that's where we introduce IPFS. IPFS is a file system that distributes and versioning large data sets across the web. It has to be peer-to-peer because we don't want central authority to control where the data come from or which server is hosted at. So there's no privileged nodes. And all the files are stored in actual local storage of the nodes. So my computer has the cat picture, for example, and the nodes connect to each other and transfer files or other data that represents some kind of useful information to navigate through the system, which we'll dive into. So that is the overview of what is IPFS. And with IPFS, we don't need to actually connect to the original content, the source of the content, but we just need to connect to someone who actually has the content. So actually this cat is actually on IPFS, this image. And this is actually the details. There's some hash you can see. We'll dive into that later. But this is the QM cache, the CID here. QM, this long string, actually represents its identifier that represents. This is a cat picture that it represents. And a fun story. This picture was originally on Rusty's server. Rusty gave me this hash for the big little reveal, and I have to go on the gateway. The IPFS gateway, and then find where it is hosted. But what's interesting is that I pulled this image yesterday using the same address, but Rusty took down his server a long time ago, his IPFS gateway. So he don't have the picture on his computer anymore, but someone else is still hosting it. So I'm actually able to get the same picture despite the location of the source change. So that's kind of the power of IPFS in action. Okay, so I'm gonna keep going. So we don't care about where the content comes from, we just care about what it is. And this is enabled by everything we talk about at blockchain at Berkeley is hashing. What we have is we have some data, we give the IPFS, we got a unique hash that represents the cat picture. And when we give the unique hash to IPFS that represents the cat, it gives us the cat picture that we exactly want. So IPFS allows us to store data into the system and then retrieve it later with the knowledge that our data wasn't tampered, because the data has a corresponding one-to-one mapping of a unique hash. So we have the hash, it is the cat. If we have the cat, it is that hash. So that's the core idea of the content-based addressing that's different than the web, how the web works these days. Okay, so I'm gonna go into like a user experience of how you actually use this file system. So let's say I have a cat picture. I put in IPFS, I register into the system. It gets a cryptographic hash that represents, okay, this is a cat. It's a long string. It starts QM and then blah, 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 some numbers and letters. So it has a unique ID. And then if there are other people who has the exact same cat on the network and they have the same unique identifier, then we know it's the same cat. So we'll just say, okay, this is actually the same cat, just at a different location. People have different multiple copies of it. Maybe I have one, maybe Rusty has one on his computers. Then people actually are interested in the data. So I like the cat picture. I actually store it. Andrew might store it as well, but not everyone has to store it. But we also know who stored it then on this network. So when someone wants a cat picture, let's say Robert wants that cat picture, we're able to look up across the network, see who actually has that picture on file in their local storage. And then we can find that cat picture and give it to Robert. But finding a cat picture using a hash is kind of ridiculous because I'm not going to remember the hash. I have to find the hash from the Slack message like a long time ago. I have to dig that. So we also can have human readable names that we can type in and correspond to the hash. I think Nishan has a question. Are there worries that storing dangerous data in IPFS like malware? We will talk about it later, I guess, about security vulnerability at the end. So stay tuned for that. And I think there is some malware actually stored on IPFS these days. If you look on Wikipedia, that's what they said. Robert says, how I guess does someone get a hash to search for item before they even have the item? Yeah, so we are looking into how we can actually use a human readable name to actually reference that. Okay, all right, Robert, we'll talk about it later. Cool, so let's dive in. You can actually download IPFS. I downloaded it yesterday, and this is what it's looked like. It's not stable, but feel free to play with it. Okay.
All right. Yeah, so let's talk about some predecessors, because like we mentioned, IPFS is sort of like the culmination of some really important transformative technologies. Namely, yeah, and so they even mentioned this in the paper, right? This is pulled right out of the paper. That says IPFS synthesizes many of the best ideas from the most successful systems to date, right? And so the core four are distributed hash tables, block exchanges, version control systems, and self-certified file systems. And we'll go into each of those in detail. So to start, we've got distributed hash tables. So what is a distributed hash table? I remember when I first started learning about this, just seeing the words like distributed hash table, DHT, I was like, whoa, this seems like some high level stuff. Like, I don't know. It's really not. It's pretty straightforward. If you guys are familiar with hash maps or Python dictionaries, like just think of that. But now all of our entries, all of our key value pairs aren't in one place. There's just kind of subsets of them split across a bunch of different computers. And these computers have some way of talking to each other. So some like network protocol. And so we have a hash map, we split its key value pairs across a bunch of computers, and we also include some information / an algorithm for like when I want to find a given key, how do I find the node who has it? That's all that a distributed hash table is. Like info for finding peers and split up key value pairs. But there are a number of implementations of this that have been like particularly good at what they do. So the most I'll preface these by saying like probably the first big distributed hash table in the space was called Cord. And if you're interested in this and you maybe want to learn more about distributed hash tables, generally I'd read about Cord. It's pretty readable, it's pretty understandable, but sort of like the big boys now are Kademlia, Coral, and skademlia. So Kademlia, we're not going to go too far into it. It's got efficient lookup. You only need to contact, like whenever I want to query some data from it, you only need to contact on average like log of the nodes, something like that. But one weird thing with it is that obviously whenever you're trying to search for content, you want to minimize how much searching you have to do. And so in distributed hash tables, usually you have to go from like node 1 to node 2 to node 3 to node n until you actually get it. And it's all about like reducing the distance of your search. Like when I query the first node to when I query the last node, I want to minimize that. And so Kademlia isn't particularly elegant because they use they basically just say like every node has an ID and the XOR of two nodes IDs is the distance between them. Don't have to think too much about that. Just basically like if IDs are pretty much entirely random, then you can think that notions of distance between two IDs is also pretty much random. So there's poor like geographical locality basically in this. Like I might say like, I want the photo of the cat. Let me reach out to node 1, then node 2, and then I'll get the cat. But maybe like node 1 and node 2 are on different sides of the globe. Kademlia has no idea, but that's not really good for me because now there's latency. So next we've got Coral, which tries to address that issue of data locality. And so what it does is, sorry about that. So in Kademlia, we're actually storing the data itself, like the bits, the ones and zeros of that cat image are in the key value pair. They're like in the value. Coral is a little bit different where it says, we don't really need to do all of that. Like similar to IPFS, nodes can just store content locally, and then this distributed hash table will just say like, for a value at this key, we're just going to return one of the nodes that has this value. And the Coral calls itself a distributed sloppy hash table because it doesn't actually need to, like for a given key, it doesn't need to tell you everything that it has for that key, which would be all of the nodes who store that data. It just has to give you one of them. So it combines that like we just need one of the nodes that have the data with this clustering system where they basically like geographically organize nodes so that first you reach out to like close nodes and then you like spread out just to like optimize on how long it takes to find something. But that's really the difference there, right? So like Kademlia is basically like more or less a classic distributed hash table. Coral is saying like, oh, let's introduce geographic locality and content addressing basically instead of just content itself. And then finally we have Kademlia, which says like, oh, there's a couple security issues with the original Kademlia implementation, namely it's not Sybil resistant. Like I can just create a bunch of nodes and spam the network, force DOSes, force eclipses, things like that. Like I'm sure I don't have to go into the details here and you guys understand that the ability for Sybil attacks is exploitable almost everywhere. So it's good that we take it out here, right? And the way we take it out is saying like, if you want to make an identity, if you want to make a node, you have to run proof of work. It's going to be computationally intensive. And the other thing it does, which is like a little more in depth, is disjoint lookup paths, which just basically means like, let's say the cat photo is out there on this distributed hash table and I want to find it. A lot of distributed hash tables will have like a deterministic path to get there. Like I want the cat photo, no matter which node I am, my search will always start with the same node 1. My search will always proceed to the same node 2, etc., until we get to the final node that like has the content. And so what Kademlia says is that for any piece of data that's out there, there's basically like multiple paths of nodes that we can contact that don't intersect. Like I could ask Niche then Gloria to get the content, or I could ask like Seon then Simon to get the content. And what's nice about that is like it prevents routing attacks where like, let's say Avengers Endgame is out here and everyone wants to download it and I'm the one node that everyone has to go through to get Avengers Endgame. I could just be a piece of shit and be like, you've got to pay me $50 or I'm not going to route you to the content. So that's how Kademlia addresses routing attacks like that with disjoint lookup paths. But big takeaway from here, right, is like, let's take a hash map, let's split it across a bunch of different computers, and then let's just have some way to like find the values in these different computers. That's all you have to know about DHTs.
All right, awesome. So another previous predecessor IPFS looked at is BitTorrent. It's probably the more popular peer-to-peer system that people still use these days. You might use them for downloading your movies, which I don't recommend doing that for copyright reason, but you might have in the past. But to understand how it works, there's two central principles that we have to look at. So let's say I have a copy of the Avengers Endgame movie, and I have the entire file, and Andrew wants it. I'll look at I'll tell Andrew that I actually have this movie, and Andrew will tell me that he wants this movie. But I don't simply give him the movie. I look at if he gave me something in the past. if Andrew has asked me for movies for the past, I don't know, a long time, and he never gave me any movie in return, I'm not gonna let him to get the data he wanted. I'll start choking him out and stop sending him a lot of data about the movie. But if Andrew actually sends me a lot of other things, I will actually give him the movie really quickly. So you get rewarded if you contribute to the network, and this is how the peer-to-peer system keep people from like sharing resources and like making sure activities happen across the network and people are sharing with each other. The other key thing is that it prioritizes the rarest piece of the file. So let's say maybe mgame MP4 is actually very popular and like everyone has it. So it's actually not that rare. But what's rare is, for example, like a French subtitle file, and only like I have it maybe. So when Andrew wants it, I'll actually send, when someone wants it, then we'll actually prioritize that because it's much rarer. It's determined by the algorithm. And so that reduce the bottleneck for availability of the system. And we are able to make sure the rarest piece of the file are first to stand out rather than some of the more common files in the system. So that's BitTorrent, and these two principles are very important and will be implemented in part of the IPFS protocol. And another thing is Git, that very popular distributed version control system. And IPFS is very ambitious. They want like make a version control system as well. So they look at how Git implemented using the Merkle-DAG object model, which is very essential for how IPFS develops its entire file system. And if you notice that Git has every commit you have has a hash, and all the files and all the differences have a hash. It references to it represents the contact address approach we talked about in our previous example with a cat picture. That we really care about what represents a file rather than where it is. So Git uses that, and using a DAG model to hash them up to store these content addresses, a representation, the hashes of the content. And it's very inexpensive to share and send to another location. You just need to copy all the metadata and update the remote reference, and you're all good to go. But the key takeaway here is that Merkle-DAG is very important. We all know about Merkle tree from Bitcoin, but Merkle-DAG is a little bit more general, that it doesn't have any balancing requirements for the tree, and every node can actually carry some data. So every node has some data, and also a list of identifier, which is the hashes of its children. And the hashes are representing of the content addressing approach that this takes. And we call that hash the node identifier, the CID, which you will see in a lot of the IPFS portals and command line interface that will show CIDs. And there's a self-verifying structure that it shows, okay, I actually store these data because the hash represents what the content is. So that's, but layer by layer, it's self-verifying. And this is important because the central IPFS principle is to model all the data of the file across the network as the same Merkle-DAG. And we'll dive into that later, but just keep this in mind.
Yep. And so the final like predecessor technology, now this one was pretty tough for me to wrap my head around. So if you're feeling the same, don't worry about it. And we can definitely talk about it more in depth offline. But it's this notion of self-certifying file systems. The sort of problem tackled by this technology is that, if there's a remote file system that I want to access, which let's consider a website to be a remote file system because it's pretty much the same thing. So if there's like some remote resource I want to access, how can I be sure that the location that ends up sending it to me is right? Like actually owns the file, basically. Yeah, that's what we want to verify, because if I start getting this file back allegedly like from some location that doesn't truly own it, like it might have been corrupted, there's security issues there. So basically, like, can I make sure that I'm getting my content from the right place? And the idea here is like, okay, let's identify the content by the place. Like, let's tightly couple what the files are and who is allowed to serve them. Namely like this. So the address scheme is this like location : host ID, where location would be like, www.server.com, and host ID would be like slash, name of my file system. So just think location, website, host ID, name of file. And the interesting part about the name of the file, the host ID, is that it's actually generated by signing a concatenation of the public key and the location, which just means like basically we combine the public key, like the creator of the content's public key, right? So that's like the key pair in question here is like someone made this file that is being hosted remotely. They have a public and private key. So when they make this file or this file system, they sign its name or they make its name to be a signature of the public key and the location where it's meant to be hosted. And why is this helpful for us? Well, so let's say I know that I'm looking for the file that is named host ID, which is already an assumption, right? Like however I did, somehow I got that name and I know it's what I'm looking for. And now it's my job to figure out like, okay, who can provide this content to me? Maybe I search up online, right? And I find out that, oh, apparently this website location claims that they can give me the content that I want. Okay. So what you'll do then is to say like, okay, website, to prove that you're about to serve me the right content, why don't you send me a public key for it? And then when they send you the public key, what you can do is you can use the public key to decrypt the name of the file system because it was signed with the accompanying private key, right? So you use the public key to decrypt that file system. And then basically you check like, okay, and in this decrypted file name, does the public key check out with what they've sent me? And does the location check out with what they've sent me? So that this way, like, even if a fraudulent location tries to send you the right public key, you'll know they don't actually own the data and you might know not to trust them in future communications. If a fraudulent location tries to send you the wrong content, you'll know immediately, which is really nice. And so, yeah, it's basically just a way of saying like, if all I know is the name of the content, I can still be sure I'm getting it from the right place. And IPFS relies on this as well because at the end of the day, like what do we pull out of the DHT that we actually know? It's the name of the content. And then what do we end up doing? Well, we end up finding a node that has the content. So we have to be sure that the node is like authorized to own it and host it. Again, don't get too caught up in the weeds here. If you guys are like me, you're probably like running this through your head right now. Like, does that make sense? Is that actually secure? I will leave that as an exercise to the reader, but honestly, just know that like we can authenticate content based on its name, pretty much. Okay, so those are like some of the predecessing background technologies, but now let's look at the actual like components and modules that IPFS has set up. And just to preface this, they say this in the paper as well, it's not like very clean abstraction boundaries between each of these pieces. They all, intercommunicate and interact. So it's like kind of arbitrary distinctions, but these are like more or less the different parts that we're concerned with. Simon.
All right. Yeah, so we learned about IPFS. Its functionality seems very, very ambitious. There's a lot of things I want to do. It has to be distributed. I can find the file even in a partition network. I know who I can find that file for, and then I can validate that file is actually that file, and I can do version control on it. There's a lot of things that go into the system. So let's think about what components we need to think about to make the system work. So first, it's a distributed network. So we need a network. So we kind of the paper divided into these sections, but we modified their kind of priorities to be like from lower stack to like more abstractions. So on a basic level, we have network identities and objects, and the network is we need to connect the peers, the nodes, to each other, and they have to send messages to each other because that's how a distributed system needs to communicate. And traditionally, for network communication, we can use HTTP, HTTPS, you can do WebRTC and all that, but we will dive into how IPFS try to account for most compatibility with all kinds of network protocol and make sure peer communication and management is very effective. And then we need to know who are actually these nodes. I can label my computer as computer number 1, and Andrew can also label his as number 1. Then we all got confused. So we have to make sure we all have unique node identities, and we can actually verify that it is a true identity. We also want to make sure people just don't spin up like hundreds of nodes all of a sudden, and we have to put some limitation on that. So traditionally in a network system, that'll be the IP address, IPv4, IPv6 address of where's my computer in the network or global network. So we have the identity of the node, we have the network that's connecting them, but what are we transferring? We're transferring data, and we want some kind of a representation of the files. And as we talk about in the predecessor and how IPFS think about the best way to represent a lot of data, they think Merkle DAG is the best way to do so, and we'll dive into why that's the case and how they structured it. So that's the data they're transferring, and the Merkle DAG, it will represent any arbitrary data structure, whether it's a movie or a picture or audio. They will all save it in the Merkle DAG to kind of some kind of representation. So now we have the basic layers. What we're transferring is the cat picture, and we also want to do version control on the cat picture. So then we need something similar to Git that we can use the DAG to track the differences over time, what's modified, and yeah. So basically, we're trying to have version control on the system, on the data that we're transferring, on the files that the nodes own. And traditionally, we don't do data, we don't do version control that well on traditional web system, but we have the files. It's HTML, it's a TXT, it's JSON object, it's whatever. But here we're trying to make a version control system that works for any kind of files on the network, which is very ambitious too. Now back to our early example, I need to know how can I visit another node? Let's say I know Andrew has a cat. I need to know how to get there. And I need to go through all the network and see who has the cat and how can I get it. So we need a routing system. And traditionally we use DNS for that, but here we're trying to use a distributed hash table for this. And we'll go into how that's done as well. So we want to have a list of the peer addresses and also able to retrieve them, update them, and go to wherever we want to go. So we're transferring files, we're doing version control of them, and we're going around the network. We need to think about how to make this more usable. I think Robert asked earlier that we're not going to remember the hash of the cat or whatever images. We need to come up with some kind of a permanent naming system that, for example, it's kind of like a pointer in a Git repository, like master points to that object or that commit. We want to have a permanent naming system, and preferably that could be self-certifying. So Andrew talked about SFS earlier, and they use part of that technology too. And traditionally, we just traditionally in the web we use HTTP and HTTPS location for the file that we're trying to go to. But here, since we're not doing the location-based idea, we need to come up with something new that we are able to come up with a permanent naming approach that we can don't have to type in the hash each time, because the content, when the content updates, the hash also updates, so we lose track of it. So we need some kind of pointer system, and also we want preferably human readable names that we can search up in the network, because I don't want to type the hash is very long and I can't remember it. Okay, the last part of the puzzle is the exchange, because I need to know actually Andrew has the cat and actually I need the cat. So we need to figure out a way that brings these information together, and we're able to create a market that we are able to distribute files across the network. And we talk about how BitTorrent does this, and IPFS come with something that's similar to BitTorrent, but also a little more advanced. So Andrew will dive into how that incentive system is going to work as well. But we need to create this kind of market mechanism that we can tell each other what we need and what other people have, and we can exchange files on the network. So that's basically the high-level overview of the puzzles, the pieces that make IPFS work. These are like kind of like the sub-protocol of the larger IPFS protocol, which is quite complicated.
Yeah, and now we're going to see how it all comes together. So we're going to take like a closer look at each of those 7 pieces listed just now. And hopefully, like this is going to be meaty, but hopefully you'll have some question answered and at least get a little bit more insight into the gears and levers and the bells and whistles and everything that make IPFS work. So to kick things off, the network, right? This is really like, what am I using to send messages? How do I get like from node 1 to node 2, right? And what's cool about IPFS is that it's very, very flexible about this. So it has no preference for what messaging protocol you use. It doesn't have to be HTTP, like doesn't have to be websites. It doesn't even have to be IP, which if you guys aren't familiar with it, admittedly, I'm not even super familiar with the modern networking stack, but I know that there's like a bunch of different protocols that all basically at the end funnel through IP as like a data format. IP is pretty much just a data format. So like HTTP uses IP, WebSockets use IP, WebRTC data channels use IP, SSH uses IP, right? But IPFS doesn't need to. And you'll see this. So IPFS is really trying to set itself up to be future proof. Like if there are changes to the data standards, IPFS wants to stick around. So that's why it's completely flexible in terms of what transport protocol you use. It's best suited, that being said, for WebRTC data channels or UTP. UTP is like a variant on HTTP that BitTorrent made. The point there being that like it's better suited for these like data media that are, suited towards streaming content. Like in HTTP, for example, when you're downloading a file, it's sequential. It's like, let me get the first byte, the second byte, etc. With BitTorrent though, or WebRTC, actually, I'm not going to speak on WebRTC because I don't know, but with BitTorrent, it's like I can get byte 1, 4, and like 43 and just download them in parallel and put them all together in the right order later. And so IPFS definitely plays better with those sorts of transport protocols that aren't confined to like the strict serial sequential format. Because, one of the bigger use cases of IPFS is downloading large media. So that being said, it also does a little bit more work, right? On top of just like, do you use HTTP or do you not? It'll do some connection management for you. This is something that's typically handled by the transport protocol. So for example, reliability. That means like, let's say I'm video calling Simon, we've got like a stream of data going and we start losing packets like somewhere along the list of nodes that my data goes through, the list of servers, in like the typical internet, somewhere like my bits are falling through, right? And so typically like the transport protocol will handle this, like TCP, which is basically like what you use when you're on the internet. It will run its own checks to say like, okay, did you get all the data from me? Do I need to resend anything? And so if you're using a protocol that like doesn't do these checks, IPFS can put a layer on top that'll do that for you. Similarly, IPFS is good at like resolving addresses. Like when we're talking about the modern networking environment, there's this thing IPv4. IP is like an address. Suddenly we started realizing, fuck, like we didn't leave enough space for enough addresses. There are too many people on the internet. And so we started coming up with these hacky solutions called network address translators, just basically saying like, oh, we've got like private networks where you just have like basically like one IP on the top of it. And then there's a bunch of computers within the network that get their own smaller, like separate addresses. And we've got VPNs and we've got firewalls. And basically it's like really tough to actually like find out. It can be really tough to find out what your public IP is and also communicate it effectively to other people. So IPFS will help with that. It'll basically make sure that like once you have a node ID, an IPFS node ID, you can get to that node. And finally, there's a couple of like implied security measures. Namely, because we use like these content hashes, we can also use them to check message integrity, meaning like I can make sure it hasn't been corrupted or changed in flight. So like, let's say I want the block with this hash and then someone sends me the block and it's got the wrong hash. I can be like, you're capping, that's definitely not what I asked for. And similarly, as we're about to see in the node identity generation, every node does generate like a key pair for themselves, which means you can verify message authenticity with the sender's public key. And Robert, yes, that is why we're transitioning to IPv6. It's because there's like not enough space left in IPv4, and the solutions that we're coming up with are like pretty hacky. So yeah, good catch. Yeah, IPFS could be another solution. Yeah, IPFS is more like it'll work if we do IPv6 or if we do something else or if we do both. But let's move on. So that's network. That's basically like I like thinking about it as a language example when you're trying to like speak to someone, right? Network is what are we using to communicate? Am I talking to you face to face? Am I writing you a letter? Am I on the phone? Am I on email? Next up, we've got identities, which is like, who am I talking to, right? And just to finish out the analogy, I'll spend more time on the slide. In that core stack of like network, identities, and objects, the last piece of that analogy where like network is, again, how are we communicating, talking, texting, etc. Identities is like, who am I communicating with? And finally, objects, I would say, are like, what language are we talking? What's like the agreed format? But so I don't know, if that analogy helps you, then you can keep that in mind. If not, hopefully it's straightforward enough. But so moving on from network, we've got this notion of an identity, right? Like what is a node in the network? And I don't intend on showing you guys a lot of code in this presentation. There are a couple slides that have it, and this is one of them. The only reason I include it is because it's one of those cases that I think it shows how simple IPFS is under the hood, or can be, and I think it just shows how elegant it is. And this obviously also isn't real syntax. It's just like, don't worry about it. So when we've got a node, there's really three fields that we care about. There's an ID, a public key, and a private key. And if you notice that like multi-hash type, so IPFS, like we said, they're trying to be future-proof. So they're saying we don't care what hashing algorithm you use. We've defined a multi-hash type, which basically says like you have to tell us which hashing algorithm you use and then the hash. So this multi-hash here is from the cat photo. And you can see there's like a couple header bytes there, which say like what hashing algorithm and like what format, and then it has the actual hash. So if that was confusing to you, why it's called a multi-hash, that's why. But all we need though is an ID and then a key pair. And then to make sure that we can't just like Sybil attack the system and spawn a bunch of nodes, we have a proof of work based node generation. And so hopefully if you remember like the proof of work pseudocode for Bitcoin, this should be a little bit familiar. Where like, you know, there's some number of zeros that your hash has to start with for it to be considered like of sufficient difficulty or accuracy. Like we said, like, you know, computing hashes is throwing darts on a board, and difficulty is just like making the board smaller. But here, so like in Bitcoin, we used a nonce, right? We'd have all of the block content, and then to add in a bit of randomness that would change the hash, we would say, here's a nonce. Now in IPFS, the nonce is just like your public key. So what we do is like, until we hit the difficulty threshold, we just keep generating key pairs until the hash of the public key basically like fits the difficulty constraint. And so there you go. Why don't we want people to spin up more IPFS nodes for fear of some kind of denial of service attack? So Onkar, pretty much, yeah. And I don't want to give you specifics because I'm not super sure on the exact DOS attacks that are possible. But for example, so like we got this idea of let's use proof of work to make nodes from Escademlia, which is one of the distributed hash tables. And the reason Escademlia does it is because there are, for example, like Eclipse or routing attacks where, let's say I know where Avengers Endgame is on the distributed hash table and I want to block people from getting it. Maybe I can just spin up a bunch of nodes, and maybe I can even like do so in a way such that their node IDs put them in the lookup path for Avengers Endgame. I can just keep making nodes until I occupy like enough of the lookup path that I can essentially eclipse someone from getting the content, if that makes sense. If it doesn't make sense, I can explain in more detail offline, but like that's an example of an attack where like if we're not careful about making new identities, someone can maliciously make new identities to block off parts of the network. And so Ryan asks, is the difficulty always the same or does IPFS slowly increase it? Ryan, that's a really good question. And I'll be honest, I don't know. They didn't mention difficulty policies in the white paper, but I would assume that it's also dynamic, maybe dependent on like the rate of nodes going into the network or the rate of the distributed hash table being populated. Short answer, I don't know. But so again, just to like quick review, what do we need to represent an identity? A key pair and a hash. That's it. Moving on. We've got objects. This is like a really meaty part. This is like the core building blocks of IPFS. Every piece of data that exists in IPFS exists in this Merkle DAG as an object. And so before we go into it, I just like reminding myself, because this always like escapes me from time to time, that like, again, at the end of the day, all objects in IPFS, everything that is in this like global Merkle, oh my God, I forgot what DAG means. Directed acyclic graph, Lord. So everything that's in that at the end of the day is stored on some actual computer. It's not like, you know, it's on a server in the cloud in this DAG. Like, no, like at the end of the day, it's just like a structure stored on a computer. But what the structure looks like, right? And I love this. I think it's so elegant and so beautiful how like we just need these two very simple data structures to represent literally everything in IPFS. And it's literally just edges and nodes, right? So an IPFS link or an edge, it's got a name if you need it. It's got the hash of the object that it points to. And that's where, this is like us seeing content addressing an action, by the way, right? Like we just take a hash of the content and that acts as the link. And we've got a size just because that's like good to have, the size of the object that it points to. And then finally, when it comes to the object itself, so this is like a node in the graph, literally all it is raw data, which I've written in as a byte array here, but like just raw data, right? And then an array of link objects, which is just like all the other nodes I point to. It's as simple as that. And so just to elaborate on content addressing, because it's worth like, you know, enumerating some of its properties. There's some interesting things that fall out of it, right? First of all, tamper evidence. If I am used to, you know, accessing my object at, you know, like IPFS/hash, and then one day I go there and it's gone, or rather, okay, that's for like lower level technical details, that's actually not very accurate. But point is like, let's say I have like a permanent address that leads to my object, and then I can check my object's hash. Hint, that's possible, and we'll talk about it. Let's say I like use that address and then I come back one day and I realize like, oh my God, my object's hash is different. I can realize that then that like it's obviously been tampered with because it's based entirely on the content. Another thing this means is that we can deduplicate objects in the DAG. So that means like, let's say I have that cat photo and I'm like, oh my God, this cat, you guys, like, oh my God, it's a great cat. Everyone needs to know about this. I'm going to put it on IPFS and the world will love me. But, you know, I'm unfortunately not the first person on the internet to discover how great cat photos are. So maybe that cat photo is like already on there on IPFS. When I upload, it's not going to make like a new node somewhere. It's just going to be like, oh, that address actually already has like an object behind it. And what it'll do is basically just like add me to the list of peers who are hosting that object. So we never have like two of the same entity or two of the same object in the DAG, which is nice. Oh, but don't let this confuse you, because this confused me too. It's like the object itself might still be copied across a bunch of different nodes. Like I might have the cat photo and Simon might have the cat photo and like Robert might have the cat photo. But in the Merkle DAG representation, there's just one node that represents the cat photo. But that's all it is, right? It's just edges and nodes, and it's just these data fields that you see here. That's literally all you need. And you can, I'm sure, imagine how flexible of a system this is to build arbitrary content and data structures on top of it. You can make file systems that are version controlled, which we're about to talk about. You can make traditional key value stores and like hash maps. You can make relational databases. You can even make blockchains, which I'm sure we all love, right? because I mean, you've got the nodes and you've got the edges. So there you go. And I don't know, I just think it's very elegant how literally all you need is a link in an object and you can make whatever you need with it. But IPFS did decide that like, okay, while this like base level, like the building blocks of data on IPFS, it's good that we've built them out, but maybe if we want people to start using this thing, we should start them off with like a default implementation. And so that's why on top of the Merkle DAG, they have built out a file system. And what the file system is just a specification. It's like, here's 4 objects, and don't forget IPFS objects is literally just that, you know, those 2 fields right there. Like here's 4 objects and what they should look like. And this will help you define a rudimentary file system that's also version controlled. So first we've got blobs, which is just like content, right? It either represents like a small self-contained file or a piece of a file. And it's only got raw data, no links. So that means in this IPFS objects links field, it's like empty. And in the data field, it's just like pure content encoded however you need it. Then we've got a list, which represents a large or deduplicated file. So that like the reason we need this is because there's actually size constraints in IPFS on how much data you can squeeze into an IPFS object. So sometimes you just need to like combine a bunch of IPFS objects. I'm going to call them blobs from now on. Sometimes you just need to combine a bunch of blobs with a list to represent a large file. And the deduplicated bit is honestly just like some lingo from databases. It's like sometimes in databases you will have representations of the same object in different like tables or data sources, and you need to deduplicate them or like link them together. And so basically IPFS is saying like you can use a list to do that. Like it can hold a bunch of blobs that represent the same object if you need to do that. But point is, it's just like, it's also just content, but you can store more of the content in a list. However, like in terms of implementation specifics, its data field is actually like empty, or it just says like, here's the object types that I point to. And then its links field holds a bunch of links to either a blob or another list. One thing that confused me when I was looking at this is I was like, oh, okay, I feel like with lists, I can already create a file system because I can just like have blobs be files. And then when a list points to another blob, that's like a file in a directory. And when a list points to another list, that's like a directory within a directory. Don't think about it that way. Just do not. Lists are never meant to be used as directories. Lists and blobs are purely content. Directories are represented with trees, which is in implementation, it's very similar to a list. Like if you were to look at the IPFS object, it's also got like no raw data. The only difference is its links have names. So now it'll link to blobs, lists, other trees, or even commit objects. Like you can store anything in a directory, right? But now the links have names. So dope. By the way, paths in IPFS work the same way that paths do the way you're used to, like folder/folder/folder. And what's nice about it is that paths will work like that regardless of the file system definition. So like even though IPFS has a default file system, paths will work like that even with just IPFS objects. Okay, and so finally, the last object definition that we have for the file system is a commit object, which is just like a snapshot in version history for either a blob, list, or a tree. And what's nice about content addressing is that like for a commit, all you need is the content hash, right? Because like that version of the object with that hash will always exist on IPFS. So you just need to take that hash and store it in a commit. And so that's nice because at the end of the day, commits are also pretty simple objects. It's just like commit message, commit date, commit author, parent commit, and the object hash. But these are all stored as links. Yeah, so again, quick recap on files. Like we already have a Merkle DAG. It's got a very minimal object model. We figure files are probably useful, so let's just define files on top of this object model. And here are the basic building blocks. If anyone here is familiar with Git, it should not surprise you that this is almost a one-to-one mapping to like the Git object system. Other than Git doesn't have lists, like all files are just blobs in Git. But other than that, it's pretty much like Git. So that's files, right? So cool. We've gone from like, okay, I can message nodes. I know who nodes are. I can create, arbitrary content. Okay, I can create content that other people will probably understand because of this file system specification. And now finally, I can find people to send content through to, and I can also find people to request content from. And that's the routing piece of the puzzle. It's literally just going from, hey, I want this blob to I know who I can get it from. And this is configurable on IPFS. Like you can specify, I will use this to find peers. But it defaults to a DHT that IPFS has implemented. So the DHT that they use is pretty much just like a combination of Escademia and Coral. How it works is like very small files or very small data can be stored directly on the DHT, just like key data. But then for larger content, you will store the addresses of like the peers that can give you that content. So it's like if I want Avengers Endgame, I go to the key in the DHT for Avengers Endgame, and it tells me like, okay, you can get this from Simon, Nish, Sayon, Robert, whoever. And then like the features that we absorb from Escademia and Coral are, as we saw in identities, we've got Sybil resistant identity generation. That's from Kademlia or Escademia. We also have like disjoint path lookup from Escademia. We've got clusters from Coral for better lookup. And we've also got the notion of like storing the address of the peer rather than the data itself. We got that from Coral too. But yeah, this shouldn't leave you racking your brains too much. It's basically like we use a DHT to store the addresses of peers who have data. That's it. Okay, and now this is maybe a more complicated piece of the puzzle. This is pretty much just like self-certifying file systems that we looked at in the beginning. But now it's like, how do we implement that on IPFS? Because the problem with content-based addressing, right, is like, let's say I have my website and then I want to update my website to say that I just did a presentation on IPFS and here are the slides. Well, the issue is that like the second I update the website, the link changes, right? Because the content has changed and so has the hash. So we obviously need a way to like, behind some consistent address, be able to store an object and mutate it and still have that object like recoverable at the same address, right? And that's where IPNS, or the Interplanetary Naming System, comes in. And it does this like very similar to the smart file system self-certifying like setup. So it goes like this, like there's an object that I want to share with the world, my website. I make it and I make it with the IPFS Merkle-DAG object structure, right? So I get a hash for my object. I get a CID. And then also like this is actually all happens behind the scenes for you. So all you have to do is just say like publish to IPNS and it'll work. But what happens behind the scenes is like you take this hash from the object you just made, and then separately you create a key pair. And then what you do directly on the distributed hash table, you store a signature of, well, you sign your public key with your node ID. This should really remind you of in SFS, how we would sign the public key with the location. Now we're signing the public key with the node ID, which I'm sure you see the parallel there. And so then once you do that, that's the key, right, that you'll store on the DHT. And then under that key, you just store the content ID of your object. You just store the hash. And why does this work, right? So like the self-certifying part, I'm not going to go over that again because it works exactly the same as in self-certifying, as in the smart file system. And if that's still confusing to you, that's okay. It's just like not worth spending time on it here. We can talk about it. But the really, to me, the key part here is like, okay, why does this still work if I change my object, right? If I update my website, wouldn't that change the CID? And then wouldn't that like change the name that I have to access it at? The answer is no, and here's why. It's because your naming record, the record is actually like, here's the name that I want to access the object at instead of its hash. So that record is not an IPFS object on the Merkle DAG. That naming record exists nowhere in the Merkle DAG. It only exists on the distributed hash table. And so because of that, your naming record isn't actually content addressed. Its key will not change when you change the value behind that key. And that's why you can just change the value behind that key. So let's say I update my website, the hash changes. I just go to IPNS and I say, access the same key. I'd still like it to be the same address, but now just change the object that it points to. So that's why that works. Really, like the key part there is like, instead of storing the names on the IPFS Merkle DAG, let's just store the names on the DHT. So that way we can mutate the content and the key will stay the same. So that's the naming system. And also IPFS for a number of the things that they have implemented right now, they actually expect like the development community to add these features. So for example, a naming system, IPFS is basically like, yeah, like we made IPNS for consistent addresses just because like it's necessary if we want anyone to like start building on our thing. But really we're looking for someone else to build a naming system into IPFS. So if it's a little confusing to you, like it's not the final form. Similarly, like for routing, they're expecting like people will probably build their own routing solutions and things like that. People will probably build their own file systems. They just started us off with some defaults. And naming is maybe one of the most confusing ones.
Andrew, I think Omkar has a question. He has a question about the difference between node ID and CID.
Gotcha. Yeah. So yeah, sorry, I missed that. So the difference between a node ID and a CID is that node IDs pertain to computers. Like here's a machine. Here's how we identify the machine so it can talk to other machines. Whereas a CID or a content identifier is like, here's an object, here's a piece of data, and the CID is the hash of that data. So node IDs identify computers and CIDs identify data. I hope that makes sense. Cool. If there are any other questions, again, just throw them down and I'll get to them. I'm just gonna do a quick check. It does not look like I missed any others.
He has a follow-up. What if the data is stored on the multiple machines?
Then are there multiple keys? Yeah, there are. So so let's take a look real quick at like let's say we've got a list object. What does this list object look like? Well, it's it just in this links array here, it's got a bunch of CIDs to a bunch of different objects, be they blobs or other lists. So that means like those CIDs are basically like they're keys, I guess, in that sense, right? Like I would look directly for that CID. So it could very well be the case that my file, I've got like piece 1 of my file on Simon's computer, piece 2 of my file on my computer, piece 3 of my file on your computer. And technically all those pieces will have like separate keys in the DHT, but we can still access them through like the list, for example. Like the point is like, even if they're on multiple computers and even though they will have different addresses and different keys, we can still link them together in the Merkle DAG. And so we don't have to worry about like losing them. But to answer your question, yes, there will be multiple keys if it's like split up into multiple objects. So and now we're coming up on the last piece of the puzzle here. And so just for a quick recap, right? Because I know it's every slide is a lot, but like what do we have? We can talk to nodes, figure out who nodes are, represent content, find content. But now, like we've got all the pieces of the puzzle except for actually sending content to and from people, like actually sharing content, which is the whole point of the internet, right? And so that is with the exchange. It's how we share data. It's modeled as a marketplace. And so certainly the marketplace model implies like where we trade data, you know, block for block, something like that. It implies that we should use some sort of cryptocurrency to standardize the transfer of data, which is what Filecoin is, by the way. I think we might have a deep dive on Filecoin later. Filecoin is by Protocol Labs, which made IPFS, and it is like their intended implementation for, you know, how we should be using the marketplace model. But until that's done, basically they said, until we have like a cryptocurrency to represent the value of data, we'll just say like the data itself, the blobs themselves basically are like the currency, they are the medium of exchange. And what nodes have to do in this marketplace is simply maintain, for every peer that they connect to, they just have to maintain a ledger for that one peer and track the number of bytes that they've sent and received. And so it turns out this is really all that you need. Like all you need is like, and it says it in the next point, like a want list and a have list. Like I want these pieces of data, I have these pieces of data. All you need is those two lists and a ledger specification that when I like connect to another node, I know their ledger will be formatted the same. And that's all you need to actually have like a data marketplace going. But if you think about it, there's like a slight issue here, right? If we consider data the currency, then you would assume that the trades go down like this, like, okay, cool, like Simon, you've got data, great, I've got data, swap, that's a trade. That's easy with money because money is fungible, right? Every unit of money is equal to every other unit. But that's not really true when it comes to data, right? Like 1 byte of that Avengers Endgame movie is worth more in the market than 1 byte of like that cat image. So we have to be a little bit more deliberate until we have like the cryptocurrency. We have to be a little bit smart about how we can actually incentivize people to trade actively. Because the issue is that like, even though I might say like, okay, I want the Avengers Endgame movie and I have this cat image, it's not necessarily likely that I will find a block for block trading partner who says like, oh, that's dope because I want that exact cat image and I have the Avengers Endgame movie. So instead, what IPFS has done is implement like a default strategy so we at least have active trading. And the strategy is like this. It's, I will preemptively send you data if I know you want it. Like even if you don't have anything that I want, I'll preemptively send you this data just to like kind of get things circulating. And I'll maintain a balance of the number of bytes that you've sent back to me. And so then I can see if you have sent me very few bytes in return, I'm less likely to preemptively send you data. And what this means also is like, if someone has been preemptively sending me data and I realize I'm indebted to them, and maybe like, you know, we've got a great relationship. Like this is the website I always get my movies from, but they've been sending me a ton of movies. And if I don't start sending them content back, what they'll do is start like tapering off how much data they send to me. Very similar to BitTorrent, how you'll get like choked out. Whereas I'd say like the slight difference though in BitTorrent is that you are looking for like one-to-one or block for block data exchanges where like peer one wants this block and you have that exact block and you guys swap. That's what happens in BitTorrent, but here we just say like, let's do this preemptively. Let's sort of like lend data to one another so that we can just have like a circulation. And if you're interested in the specifics, like the trading strategy is very simple. It's like we just maintain a ratio of bytes sent to received, or rather, sorry, bytes received versus bytes sent. And you can see in the graph here that like after this ratio crosses 2, we severely drop off the probability of sending this other peer bytes. So that means like once I'm communicating with a peer And it's gotten to the point where I'm sending them twice as much stuff as they're sending to me. Past that point, you've got less than a 50% probability of like sending them data preemptively. But this is all the defaults, right? Like by default, we're going to consider blobs and just like bytes of data to be a currency. And by default, the trading strategy will be that you like just maintain trade balances with all these other peers and act preemptively based on the trade balances. But again, IPFS is really hoping the developer community takes off on this one and starts building their own trading strategies. So like, for example, in BitTorrent, there's also the rarest piece first policy, which says like, oh, let's get like the rarest pieces of a given file out into the network first because we want to incentivize like seeds to like pick up a full version of the file. Point is like strategies like that don't exist here yet. All we've got is just this sort of like credit system. And this is really a cool opportunity for people to come in and start building trading strategies, either on top of Filecoin or on top of the exchange. And so just a quick note on this too, because I think it's good to differentiate. The ledgers that we're talking about here are different from cryptocurrency ledgers. Like right now you might be thinking like, oh, ledger, oh, trades, what's the consensus algorithm? Where's the blockchain, right? Like what's the validation? We're not thinking about it like that. We're not maintaining a global ledger like Bitcoin does, like Filecoin will. Filecoin will maintain a global ledger that tracks all transactions. Right now, we're doing a much simpler peer-to-peer system where it's like, I find the exact peer that has the content that I want. We open a ledger together. And every time we communicate, what we do is we check, does my ledger exactly match yours? And if it doesn't, we'll either zero it out or just refuse to trade. So that way, like, yeah, you don't really have to be worried about attacks or double spending, because if it looks like a malicious ledger, you can just refuse to trade. And there's also not really a notion of double spending when it comes to pure data, because it's like, you know, I would care if you duplicated that Bitcoin and the Bitcoin was fake. I don't care if you duplicated the data you just sent to me. Like content is content, right? So you don't have to worry about double spends. But this ledger system will be replaced by Filecoin anyway. So again, that was a lot, right? But that's it. These 7 pieces are all of IPFS: the networking protocol, the identity system, the data representation are like the key parts. And then on top of that, we build a file system specification. You can also build your own. We build a routing system. You can also build your own. We build a naming system. You can also build your own. And we build an exchange. You can't build your own exchange, but you can build your own trading strategies. And that's it. That's IPFS.
Yeah, awesome. So now we looked at how it works. What I want to talk about is, you know, why does it matter and what's the unique property these technology stack bring together. So the most unique thing is that even the original publisher of the content is taken down. The content can be still served by just anyone who have previously downloaded it before. And that's really powerful because a lot of content are taken down due to like no one's just maintaining it, or censorship, or just like somehow the server broke or something. But as long as someone has it, you're able to get it. And you are getting the content that's actually cryptographically verified. You are getting the cat picture you wanted, and it's not being changed. This is the content you want. And what's even cooler, if we go back to our previous example, the first example was Earth and Mars. Let's say, you know, I mean, you can still communicate between Earth and Mars, but it's just gonna take forever. So we can think about it as a partition network. It's more, if someone has like pulled up cat picture on Mars already, you can just ask the person on Mars rather than going all the way to Earth and then get the server and to send the picture and then get it back to Mars, which is gonna take forever. So in these kind of partition networks, it can work really well. And I mean, the Mars example is very, that's a little bit extreme, but it could be like you're in an area that got internet that's partially cut off or censored, or just really bad connectivity in like some countries in the world that you're able to get content from local. And that is what current internet cannot do. So and even if some of the content disappeared, let's say the cat picture accidentally disappeared, which we tried not to, but if it disappeared, and we can't access it, but if someone added back, we get the cat picture back, which is really awesome. The nice other thing is that you can't really block IPFS. Like for, let's say if a country want to block a certain platform, you can just block the server address to it, the DNS, but here, if you shut down one IPFS gateway, there's going to be another one open because someone downloaded the file and then that other person downloaded it, and then you just have a lot of gateways. So you can't really shut it down. And even better, it can be read anonymously. It doesn't need DNS or certificate authorities. So that is good for the users as well for some circumstances. But it also is good for the internet service providers because when people are like downloading the content from a place, they're also helping distribute them. Right? If I get a cat picture, well, a cat picture is small, but if I get the end game movie from a server, it's pretty big, but I can help distribute it so that server doesn't take as much load, and that is really that lightens the entire load from a central point in the network to everywhere, and that's going to speed things up a lot. So that's some properties, and to summarize what they can, in conclusion, it is harder to attack the system, and it's easier to distribute files that otherwise you could miss or is deleted or you have no access to. It's distributed. You don't need a backbone of the web to rely on the connectivity, and there are more people in the world will be able to use the limited connectivity they have to access more files. It's content addressable. You guarantee the integrity of the file, and you duplicate it across the network, which we talk about. We talk about censorship resistance, that it's probably impossible to shut down every single gateway to the files. And that's great for archiving because it also has a version control system. So if a lot of you use the web archive, like the website that shows on what day website shows what, this is great because you can just go back to every version of it and see what the past happened. And even the website got taken down, you're still able, probably someone has a copy of it so you can get to it. And surprisingly, it is fast. And that's important because if we come up with a system that's distributed and all that, like Bitcoin, but it takes forever to buy a coffee with it, no one's going to use it. But here it's actually really, really fast. They said that it can probably increase video streaming like 60% of the speed of it by distributing the high volume data from different distributors rather than a single point of distribution. And that actually cut a lot of costs for, like, let's say if Netflix wants to host a movie on a single server or a single data center, they have to ensure that capacity of the data center is great enough to stream to thousands of users. And actually, I think during COVID, they slowed it down in Europe. So it's not HD, it's a standard definition rather than HD because they just can't handle that much load. But if you make it distributed, then you are going to lighten that one central point a lot, and you're going to have higher performance and lower cost, and users' experience will be better. And for a little bit touch on blockchain stuff, on-chain storage is very expensive for blockchain applications, but IPFS offers a way to store very, very large files, but still in a distributed fashion that's not centralized, and we'll touch on it later. But these are some of the key advantages that you can use in your use case. So I'm going to talk about a little fun example of how IPFS has been used in the past. In 2017, the Turkish government shut down access to Wikipedia, and no one can access Wikipedia anymore. So what IPFS did is they took the snapshot of the entire Wikipedia onto IPFS. And it's read-only, so everyone can, up to a point, I think up to sometime in 2017, they have all the websites that are in Turkish on Wikipedia, they put in IPFS, and readers, when they download the page or view a page, they actually serve it as well to provide to each other. Then they're able to, in a short time, they're able to get Wikipedia all over the place, and there's no way to take it down. And Wikipedia and them are looking into how to make Wikipedia entirely distributed. So there's just no central way to block it, and how we can read. And now it's read only. Writing to it will be more complicated because you have to look at, which version should we take, who should write it, set permission, consensus. But yeah, this is already being used, and it's really great for archive of knowledge and that's just like censorship can't even do things about it. And the address here on the bottom, that's the IPFS address of the Wikipedia in Turkish. Cool. Another thing is we talk about blockchain application. Blockchain applications are horrible at storing large amount of data. Actually, if you store a 2 megabyte photo, you're gonna cost like a couple $1,000 on Ethereum, like in USD. It's just very inefficient, and I could probably buy a car with the money I want to store 2 megabytes of picture on Ethereum or on blockchain. So what we can do is we can store this on IPFS, and we remember the hash, the CID we give to the data. We can just store that little hash, which is 46 bytes, into the smart contract or whatever this application, what ledger we put in the blockchain. That then is much cheaper. We can still link and verify that content based from the hash we store in the Ethereum blockchain, but also just take it out from IPFS, see if has it changed. And that is really important because let's say in CryptoKitties, the DNA of the kitties, they are stored in the blockchain, which are just bit strings. But the picture of the kitties, they are stored by Dapper Lab servers. If we want to make that truly decentralized, if one day Dapper Labs decides to shut it down, we don't have to keep designs anymore. But if we put these designs in IPFS on the web and link that design through its hash, the image's hash in the Ethereum blockchain, in the CryptoKitty blockchain, in the DApp, we are able to make sure that these images will not disappear at all in the future. And one really cool dev tool, it's called Pinata. They connect Ethereum blockchain to IPFS for decentralized applications. And they were one of the accelerator company last fall at Berkeley. So check them out. They're really cool and they're widely used for this purpose. Cool. But here brings a problem. Okay, the system seems really great, but it assumes that someone has a local storage of the file I want. Let's say the cat picture. If Andrew somehow poured coffee on his computer and he's the only one, or maybe 4 other people, they all pour coffee on their computer, and the cat picture doesn't exist anymore. There's no way to get a local storage anymore. What can we do? Then the file is unavailable, right? Unless someone find a picture again somewhere from the repair hard drive or something. So what we can do is we can incentivize people to store files and make sure they get like extra space in their hard drive. So store some files and make it available for others so others can access it. Or make sure that on a network scale, there are enough copies of the cat picture across networks. So even if 4 people spill coffee on their laptop, there are still some other files, and we'll make sure more people will store. After some nodes are down, we're able to get more cat pictures on different laptops. So we have a certain amount of cat pictures across the network. And that's what Filecoin does. It incentivizes people to use free storage in their laptop to host files. And they want them to host for a sufficiently long time, and they will get rewarded for doing that. And they also want to make sure people, there are enough people that replicate these files across computers. So there can be if one guy broke their laptop, the file goes away case. There will always be enough files in the network that people can find. And Filecoin is basically a blockchain built on IPFS Pro, the platform to create a market to incentivize people to store things, and it rewards them for storing images and other files. So that's kind of the missing piece that's there. The protocol lab is building. And I think someone will do a deeper dive into that later in the Whitepaper Circle series. Cool. And there's other areas that need work. First, we need adoption. A peer-to-peer system only becomes good enough when you have enough people on it. Because if there's only like one cat picture, no one's going to use it. We need a lot of things on it. And we also have to compete against internet providers, such as Google and Facebook and other large service providers that host, or AWS hosts all the files. So we want to make sure we can get enough users on this. And a good way maybe to reaching out people that have limited access in areas that are remote and also might be censored to visit certain materials, that these are people that actually need this system, and it's great to get adoption from them. the other thing is IPFS doesn't have a good search engine. Because the current web, you can search up a cat picture and it will come up. But IPFS, how are you going to search up a hash? Or how do you like search a cat and then the hash describes a cat will come up? So we need a search engine for it, and they're still developing on it. You can click this link. This is the IPFS search. It's really bad. You can put in a cat and then there's just like a bunch of things, but you don't know what they are. You have to download them, and then it's going to take time. But things are moving forward. Opera, the browser, actually on Android, you can type in IPFS or IPNS, the naming system, and then put in the IPFS hash. You're able to browse directly on your browser to that file. So it is getting more and more adopted, and we're going to have more integration in our browsers. But we might need to redesign our browser for this decentralized web, because our browsers are designed on the HTTP protocol. There are some I/O limitation on how fast IPFS is for downloading and uploading files. It's because there are different kind of files that are transmitting, and also there are different protocols that IPFS currently use. The networking protocols, it might the request time request size can severely affect how fast the I/O is performing. But it is getting better. They kind of fix up their DHT logic, and in the recent release in April, they got like 2 times and 3 times speed increase, and it is only going to get better. So there's a lot of areas that need work, a lot of applications to be built, and a lot of protocols to be built on top of this platform. But it could be the future of web that will meet the demand of the future. And there are some bunch of current projects that use IPFS. So you can see Pinata is here. That's Berkeley Startups Accelerator last fall. And you can see Netflix is here. So maybe Netflix one day will stream Netflix via IPFS, and probably gonna be faster, hopefully. Yeah, so it's a very new field, but people are getting excited about it. All right, that's it. Let us know if you have any questions.
Yeah. Also, wait, Omkar, I wanted to address your last question again, because I want to make sure I didn't misinterpret it. When you said if the data is stored on multiple computers, do you mean, for example, like the same one object being stored on multiple computers, or do you mean like one large file that has to be split into multiple objects on multiple computers?
Yeah, I meant the same file, but thank you for explaining the other case too, though.
Okay, wait. Well, in that case, actually, I didn't quite give you an accurate answer. If it's the same one file, then that object will have like the same one content ID / like permanent name, however you want to put it up on the system. But it'll be one key for like, that'll say like this object, but under the one key, there will be like multiple values associated to it saying like, okay, this computer has it, and this computer has it, and this computer has it. So you can basically think there's like a parity between content identifiers, which is like an object hash, and keys for finding that object in the DHT. So like even if multiple computers have the same one object, it'll just be like multiple node addresses under the same one key. Does that make sense?
There are multiple node addresses under the same key, but in the key definition, you're signing like just one node ID, right?
Yeah, so that's in the naming system, and that's an example that's saying like yeah, here you're signing the node ID because in this case, for example, you want to say like I'm the only one who can serve this object. Oh, I see. I see what your question is. Yeah, if for example I wanted like multiple people to be able to serve the content for a given CID, I think there's probably like multi-key or multi-sig like implementations we can do for that. Or, you know, maybe you can be clever about like allowing other nodes to send you the right key or signing it with just a public key and not your node ID. But I wouldn't focus too much on like the naming system specifics and think more about just like object hashes being stored on the DHT as keys. Because basically like naming system is still going through a lot of work. And I think a lot of the objects on IPFS are just stored right by hash.
Okay, cool. Thanks. I actually had another question about the naming, and I think kind of touched upon this when you went over the Filecoin stuff. But at any point, does a user have to like pay to upload information to IPFS? Like, for example, right now, if I wanted to host my own personal website or something, I'd have to like, I'd have to buy a domain name from like a DNS provider, and then I'd have to like upload my data. So I'm like, does the end user ever have to actually pay for something, or does like this implicit like file transfer thing like take care of all of those like economics like somehow?
So right now, yeah, the implicit value of data replaces those economics. Like you don't have to pay anything to put something on IPFS right now. Like what it'll look like, it'll be like, here's a blog article that I wrote that the world needs to know about. It's on my computer. Let me post it on IPFS. So now it's like still on my computer, but for whatever reason, some nodes out there are saying like, okay, yeah, I'll host it. And the way you like pay them for hosting it is because you're probably trading data back to them that they might want, or just setting up like a ledger with them so they can ask you for data later. But basically,
so
like the
like it's not the blog, right? Like it would be other data, right?
Yeah, it could be other data. It could be the blog. The point is like you pay for people to host your stuff by hosting other stuff.
Got it. Okay.
Yeah.
Cool. Thank you.
Yeah.
Thank you.
Basically, you have some needs to duplicate some resources, and they have some needs. So you just like host your stuff, they host your stuff.
Thank you. I also really like the presentation, guys. Thank you.
Thank you.
Yeah. Thanks, Omkar.